Good night, good morning, good afternoon to everybody. Thank you for joining this live. Welcome, welcome. Thank you for watching this as a video upload later on if you're doing that. Thank you so much. And please do leave us a comment if you see this later on. Yay, we are live. I'm back to the nightly live. I think for a few nights in a row, I will be doing the nightly lives. Tomorrow, I will try to do a very long live, but at the same time, it is snowing here and I have to do a few things to take care of snow-related chores. I was a little bit busy actually yesterday and today with snow-related preparation, and so hi Clicker, hello, welcome to the live. Welcome. But that is why yesterday's live was a little bit shorter. And today I'm going live a little bit later and whatnot. And then tomorrow I was hoping for a very long live, but we will see. Either way, definitely I will be live and I hope to catch many of you then. Thank you so much. Thank you. Please do like the live. Thank you. Clicker says hi. Now Sat says happy morning. Hello, good morning. Clicker says it is lucky. Now Sat says like done. Thank you so much for liking the live. Thank you so much for being here. I will cover some interesting facts about planets. Yes, Fuji. Yes, Fuji Baba. So Fuji Baba has brought me his nightly gift, and I'm gonna take a look at that right here. Make sure that he knows that he has been acknowledged. Yes, baby. Oh, wow, Fuji. Wow. Yes, Fuji Baba. Yes, Fuji. Fuji waits for my live to start to bring me his gift. Show snow. Here, 1 second. Yes, bacha. Fuji. Hi. Hi, Fuji Suji. It's okay. So I got their water and so here's the snow. A little bit of so it's nighttime here, but hopefully you can see that there is a lot of snow that has fallen in the yard and whatnot. And okay, great. Yeah, I changed their water and they have spilled some of it. Let's see. I don't know if you can. It's a little bit hard because it's nighttime. So tomorrow morning I will definitely try to go live and show you the snow. Tomorrow. So don't worry. In the morning the snow will be very much more visible, and so we can take a look then. Right now the snow just fell. I think around 5 to 6 inches are supposed to fall tonight, and we have a bunch of snow lying outside. So in the morning we can see. So let me read your comments. I always try to catch up with everybody and read everybody's chat messages and comments and everything. I also look at where Fuji is. Fuji's sitting in his little box. Hi, Fuji Babu. Fuji's sitting in his box and he brought me his gift already. So let's see your comments. Show snow. It's 2 days. In 2 days it's gonna snow for me. Show snow. I showed you the snow, but tomorrow morning we'll look at it again. POV me when I see you live. Okay. Mangalu says hello. Ajay ready. Hi. Now Sat. Thank you. So hi everybody again. Thank you so much. Oh gosh. Hello Manoj. Hello Goob24. So Group 24, Manoj, Clicker, Mangalu, Jay, Clicker, Nausat. Thank you everybody for being here. Welcome to the live. So as per usual, I will catch up with everybody. Oh, I forgot to share the live as usual. I'm gonna do that. I'm gonna do that, and then we will continue with the topic of today, which is gonna be something to do with planets. I have found a chapter in the book that I've been using, which kind of summarizes a lot of different interesting facts about planets. I will say that I'm not really an expert on planets myself, but I've been heavily relying on this book right here called Foundations of Astrophysics by the two authors, Barbara Ryden and Bradley M. Peterson. So that's what we've been relying on very heavily to learn about planets and their moons, especially in our own solar system. And also we will actually cover exoplanets from this book as well. So again, I'm not really an expert in planets, but I realized when I was covering all sorts of other topics that planets is something that I didn't cover too much on the channel and people were interested. And it is an interesting topic. So that's why you're seeing a few different live streams now on the planets. So again, thank you for being here. Welcome. Are you upset or glad to see me? Says Manoj. How old are you? I want to be, okay. Goop says, hello. I'm so sorry I have to go to be, but if you stream tomorrow, I'll be there. Thank you, Clicker. Thank you for joining and being here, and for sure see you tomorrow. And if you could please like the live if you haven't done that already, that would be amazing. Yes, can I get 10 likes? No, can I get 20 likes, because we already have 10 likes. Thank you so much. Batman is here. Hello, thank you for the emojis. Goop says YW12. Okay, I don't know what that is, but sure. You don't know astronomy. Are you a teacher? Yes. So I do know astronomy. Astronomy has many different parts. The part that I focused on myself is particle astrophysics. And on this channel, let me just recap the things that we've covered are all the way from modern physics from the 20th century, like relativity, special relativity, general theory of relativity, quantum mechanics, sort of the progression of quantum mechanics, towards more current times of physics, towards the later part of the 20th century, how things were then, particle physics, and sort of what are the big open questions in the universe right now, such as in cosmology, what is dark energy, what is dark matter. And then we've covered things like dark matter candidates from an astronomy point of view, as well as dark matter, what it means and what is its significance and evidence from a cosmology point of view as well. So we have covered significantly about the broader universe and sort of big picture type of stuff, extragalactic stuff, like the particle astrophysics lives were focused on really doing astrophysics and learning astrophysics with particles other than visible light, which generally means from sources. You learn about sources that are extragalactic. So then, as I talked about all of this stuff and people were, learning and showing interest, I realized that they were asking questions about more to do with our own solar system and planets, and I'm not an expert in that. I did not know too much, for example, about even our own Earth. Like I knew some stuff, but I was in no way sort of an expert in it. Besides also some of the other planets in the solar system. So it's been very fun actually for me to, there were things I had learned in school, and also some of the things I had learned because I was a teaching assistant in astronomy. So I did know some things, but this has been kind of a more comprehensive look at our own solar system and the planets in our solar system, all the way from the rocky metallic planets, which is the planets closer to the sun, such as us, Earth, Mars, Venus, and Mercury, which also have rock and metals, and as well as the Jovian planets or the Jupiter-like planets, which are farther away from the sun, such as Jupiter, Saturn, Uranus, and Neptune. So even though I knew probably something or other about all of these planets, I will say that we've been covering the planets much more comprehensively at a sort of both higher as well as deeper level. sometimes more high level and sometimes more deep, depending on sort of what sorts of things we're covering, and that's what these lives have been. So there were definitely things that I had either heard about or sort of knew but did not know in a lot of depth, which we have been learning from this book. So I think it's been interesting also because planets is something a lot of people relate to, of all ages, and so I've also been looking at or doing these planet lives during the afternoons as well, when the kids might ask. So let's see, when the kids might attend, that is. So I feel Monday. Hi, Roll AV. Are you a teacher? That would sounds like it, doesn't it? Yeah, look, teacher mode. I love science. Thank you. Goob24, you're in the right spot. Do you expect the present a certain age of universe and string theory? I'm 12. Oh, very nice. So this channel actually is very welcoming to a family-friendly audience, you know, children, people who want to learn, people who like enjoy kitty cats, and also who enjoy science. And specifically, my background is in physics, astrophysics, and also I love covering cosmology. So that's really the vibe of this channel. If you're new, I'll take a clip of that and I'll post it as a video as well, so that this goes through the head of some of the more dumber people here. But serious question, are you ready to make me? Okay. Manoj, my mods are not here. Otherwise, you would be banned already. And I'm too lazy to do banning at the moment. And I kind of need the watch hours, so keep on going. Thank you, Goob. Goob says, I love cats. Arlo says, yeah, I mean, whatever people feel comfortable with. My content will be family friendly. If you irritate me too much in the comments with more inappropriate comments, I will press the buttons to ban you, because my intent is that the content will be children friendly. I will be covering planets. I hope that is settling in your brain, the ones with smaller brains. So, without further ado, welcome to you, Goob24, and everybody else who is open to learning. Let's see. So we also have, before I forget, we also have covered a ton of stuff about stars, supernova, and stellar remnants. So stars have certain life cycle that they go through in their evolution. So that's another example of something I've covered here quite a bit. And, you know, depending on the star's mass, actually, it turns out in astrophysics, certain things are really hard. For example, all the sites of interest are kind of far away, right? Even within the solar system, the distances are quite large. But especially if your object of interest is not within the solar system, it's going to be even more farther away, which makes it hard to study. It's almost like you have a lab that is very far away. You can't attend it. Like, you can't wake up and be like, yes, I'm going to my lab today, which happens to be the supermassive black hole at the center of our galaxy. You know, you can't easily go to your lab in that sense, or the site of interest. So that is something as well to consider when we study astronomy. But some of the nicer things is that certain things are actually incredibly simplified by, for example, this particular fact, which is that pretty much as far as the stellar astrophysics goes, like the study of stars, right? A lot of the things that happen with stars, whether it is their life cycle, their evolution, what it will do, how it will explode, how it will die, and what type of stellar remnant it will leave after its death, is all dependent on its initial mass. So however much it, you know, whatever, how massive it is gonna affect so many things, pretty much almost everything. So we looked at how, depending on the mass of the star, the stellar remnant, for example, is either a white dwarf or a neutron star or a black hole. So that is something that we also looked at in the past, and we did a few lives on that. So if you're interested, for example, Goop24 and whoever else who likes the astronomy stuff, if you're interested, we have actually covered something like supernova and stellar remnants in the past as well in a lot of detail, or at least in a good amount of detail. So we've done all that as well. Like typically that's more the vibe of these lives, but right now for a few live sessions we're covering the planets, and I want to finish up with some interesting facts. So Goob is asking why. Can you ask what do you mean by why? Why what? How are you today? Why is Mars the planet of war? So I think the planet of war is Mars in astrology. This is more of an astronomy, astrophysics, and physics cosmology type of life. So I'm not an expert in astrology. But I do know, I think that the sun sign of Aries is ruled by Mars, which is the god of war. So if you're an Aries, you might be good at war. That's all I know. I do know a little bit of astrology, but no, by no means is that my expertise. I just wanna... Okay, Manoj, goodbye. Goop24 says why. War, I love paranormal. All right, Manoj, time out for you. I have a book about Indians. Okay. And I think I need some more ginger ale. Where are my mods today? You guys are slacking. You guys are slacking. I have a lemon in this, so I mixed the ginger ale with some lemon juice, and then I drink that to settle my stomach. I ate some Indian food that made my stomach a little bit heavy, let's just say. Okay, so thank you, James, for your input. As usual, it's a little bit out of place here, James, but we accept what you have to say, and then please keep on going. Okay. Oh, and I never shared the live. Exactly. Where am I? Okay, planets, interesting facts. That's the live I'm doing. Oh my God. Sorry, give me 1 second. I want to share the live, and as usual, my channel is sort of just science, boys and girls. Yes, thank you. I think you get it. Oh, there we go. So I had to open YouTube again on my iPad in order to... Thank you for liking the live. If we could get 20 likes, that would be amazing. I will freak out if my phone dies. Yeah, same. Usually I know that my phone is about to die. When I do these lives, there oftentimes we actually have lost the live because my phone died. Usually I have my laptop here with me. Right now I don't, but that's okay. All right, so we will keep it going, keep it pushing, and go towards this particular chapter that I found interesting, and I thought it would wrap up our planet discussion really well. And if we can't finish today, we certainly can continue tomorrow as well. So that's another option. But I thought that the authors did a really good job with, wait, now I've lost the spot. Oh, I think I'm close. I thought the authors did a really good job. Look at the pretty pictures here. Look at this. Look at that. There's so many pretty pictures. Look at this. Let me show you. Look at that. Sagittarius. So what you just saw, the caption is Sagittarius A at a wavelength lambda of 20 centimeters. So as you might know, because I've covered it in the past, Sagittarius A, of course, we have seen in multiple wavelengths. It's a source, like a radio source, a X-ray source, all kinds of things. So this image shows a region 25 arc minute across, corresponding to a length scale D of 60 parsec at the galactic center. So this is the, as I mentioned earlier, there is a supermassive black hole at the galactic center of our own galaxy. And of course, it is eating and accreting mass from its nearby objects. So that stuff that is falling into the black hole is actually a very bright source of radiation that we can pick up on. So even though a black hole is black in the sense that even light cannot escape, around the black hole can actually be particularly bright and a bright source of different signals. And that's what we see here. So Sagittarius A at a wavelength of 20 centimeters. This thing you just saw is a region 25 arc minute across, and this false color image, red indicates the highest surface brightness. So we're giving a color to the type, to the brightness here. Signs, I mean, oh, very nice. Signs and cats, I think you'll find. Basket of minks. Yes, hello, basket of minks. How are you? Okay, so then we also have Sagittarius A West in the bottom picture of the same page. I'll show it to you in just a second. Sagittarius A West, this is the picture at a wavelength of 6 centimeters. This image shows a region 3 arc minute across, so smaller, corresponding to a length scale of around 7 parsecs at the galactic center. In this false color image, white indicates the highest surface brightness. So those are the two images I just talked about. You can take a look. These are really pretty. Oh, very nice, Scoop 24. So that's a little image for you. As I flipped through to get to the spot where I want to go, I saw these pictures, and the last time I was live, I actually wanted to show these, but I had to cut it short. So here it is now. Okay, want to look at a planetary nebula? Here. Here's a planetary nebula. Look at that. Oh my gosh. This is so exciting. So this is the Ring Nebula, a planetary nebula at a distance of 700 parsecs from the sun in the constellation of Lyra. Okay. Ooh. Oh. Ooh. Orion Nebula. The Orion Nebula, an emission nebula at a distance of 400 parsecs from the sun. Here's a Hubble Space Telescope image showing a region about 0.5 degrees across on the sky. So this is the Orion Nebula. Look at that. This one right here. This one is the Orion Nebula as imaged by the Hubble Space Telescope. So here's some pretty pictures before I move on to the, text and topic today. But yeah, ooh, also because we're going to cover planets, here's some pictures of the terrestrial planets shown at correct relative sizes. So as you know, the terrestrial planets are Mercury, Venus, Earth, and Mars, and these are also called rocky metallic planets because they have rock and they have metals. They condensated closer to the sun, so we kind of spoke about this, but real quick, I'll mention that if things are condensating closer to the sun during the formation of this solar system, then it's going to have metals, or sorry, it's going to have, well, metals and materials in general that basically condensate at higher temperatures. So it's gonna, basically, it's gonna have things like what we have, which is we have an iron core and stuff like that. So we covered all of this in a lot of detail, planet by planet earlier, but I wanted to kind of mention it again. So here's a picture from left to right. It's going to be Mercury, Venus, Earth, and Mars, and it will show you how Venus and Earth are so similar in size, actually, and in mass. They're called twin planets. So it's a very unfortunate thing that Venus has a poisonous atmosphere, because I think that Venus would have been a great planet for us to, go to instead of Mars, because Mars is like farther away. But yeah, it's very unfortunate. Venus has too much carbon dioxide in its atmosphere because it did not have oceans like we do to kind of absorb some of that carbon dioxide and turn it into limestone. So in short, that's why our atmosphere is so much better for breathing. And Venus, because it's closer to the sun, it does not have water in the liquid form, forming oceans, and so it has this poisonous atmosphere that was not able to evolve to a more better, safer breathing type of air like ours did. Okay, like, because our atmosphere was something else as well. And also remember that we after we started having plants, of course plants also take in carbon dioxide and breathe out oxygen, right? So even before plants and things like that, just having the oceans on Earth really helps, because the water will basically turn carbon dioxide into limestone, and we covered that in detail in a previous live. Hi Doral. I have a cat sleep by me. Oh, very nice. We all know about Orion because of Men in Black. Speaking of cats. Oh, nice. Oh, good. I love moonstones. Moonstones. Oh. I scroll up. I see James is here. You're the best troll. Hey, hope you've been well. I've been well. Just dealing with some snow preparation type stuff. But other than that, not bad. How have you been? Is your work travel done? Okay, so here's the equation. I keep saying, I mentioned to you about Venus's poisonous atmosphere, so I just want to tell you real quick, because I know we covered this earlier, but I just want to tell you. So CO2, which is carbon dioxide plus water, if you have, of course, oceans like we do, CO2 plus H2O gives you H plus HCO3 minus. So HCO3 minus is a bicarbonate ion. The bicarbonate ions combine readily with any calcium ions dissolved in the water. So Ca2 plus 2HCO3 minus will give you CO2 plus H2O plus CaCO3. So CaCO3 is calcium carbonate, which is poorly soluble in water. So it precipitates out to the ocean floor. Limestone, which occurs in abundance near the Earth's surface, is a sedimentary rock that consists largely of calcium carbonate. So since Venus is too hot for liquid water to exist, it lacks this mechanism for removing carbon dioxide from the atmosphere and locking it up inside rocks. So literally, because we have the oceans, which is liquid water, we are able to capture the carbon dioxide from the atmosphere and lock it up in rocks. Like, we make rocks out of it, if you think about it. So we're a planet who was able to clean up our atmosphere because of this ability, because of the ocean. So the oceans are really where it's at. Without that, it's going to be really hard to make the atmosphere more better and breathable, and to encourage more life to evolve. So far, that's what we think anyway. That's what we're seeing in our solar system, at least anyway. And that's why, again, it was super duper exciting to get implications that Europa might have subsurface oceans of liquid water. So again, that's why the moon of Jupiter, one of the Galilean moons of Jupiter, Europa, is so interesting. It's a big lab topic, like a big research topic, especially at places like the Jet Propulsion Lab. So if you want to study it there, you could. It's a whole big thing because people want to confirm for real, whether it has this water or not, or how much, and like what are the different details of all these different moons and stuff, especially Europa, because especially the surface of Europa betrays that it looks a little bit like our Arctic region, basically. So yeah, thank you for liking the live, by the way. If you could please like the live if you're new here or just joining, that would be amazing. Thank you so much. So I just wanted to quickly share about the Venus thing because I think that Venus is really cool. It just has a slightly unbreathable atmosphere. And now let me show you the rocky planets. Up top here is, wait a minute. What am I doing? Yes. Up top here is Mercury, Venus, our own home planet Earth, and then Mars. So these are the size comparisons as well. The relative sizes are correct in this picture here. So Mercury, very tiny whiny. Venus, almost like the same size as Earth. Earth is our home planet. Hopefully that looks pretty familiar. And then there's Mars, the planet that we might be settling down in as well. So I just looked down and Fuji Baba is in his box. So after he has his zoomies and he brings me his toys, he will settle down. And he's like right here, he's giving me company. Fuji, Mama loves you, Babu. Mama loves you. Okay, so, and then also let me show you, because we're looking at pretty pictures, let me show you the Jovian planets, which is of course Jupiter, Saturn, Uranus, and Neptune, also with the correct relative sizes and with pretty color pictures here. And of course, another thing some people didn't know, Jovian just means Jupiter-like. So even though not all of the Jovian planets are really quite as huge or as interesting, well, I don't want to say interesting, as huge or as particularly remarkable in some of their properties as is Jupiter. But basically the Jupiter, Saturn, Uranus and Neptune are called Jovian planets, okay? And again, Jupiter is a massive. Jupiter's mass is 318 times the mass of Earth. So again, correct relative sizes is right here. Jupiter, Saturn, Uranus, and Neptune. See how these are kind of blue? These look kind of blue. That's because of their specific properties that we talked about as well. But there's Jupiter, see all the bands. We talked about these bands and the big red spot and all that. And of course, Saturn looks kind of big also because of its rings. So all of the Jovian planets actually have rings. Saturn just has the most famous ones. Saturn's ones are the most noticeable and remarkable ones. Oh, Fuji, he's all curled up. So that's what that is. And then, also, while we're on this picture, here are the Galilean satellites of Jupiter, also at the correct relative sizes. These are going to be, of course, Io, Europa, Ganymede, and Callisto. And also note, we talked about these as well. And note that Ganymede is also the biggest moon of our solar system, just period. It's the biggest satellite, period. So here are Io, Europa, Ganymede, and Callisto. So you can't see it when we looked at a zoomed in picture of Europa, we were able to see what I was kind of talking about its surface looking a little bit similar to the Arctic region. So we can talk about that again later. But basically, those are Io, Europa, Ganymede, and Callisto. And also, we mentioned how Io is the most geologically active site in our solar system. Because it is so close to Jupiter, it constantly has volcanoes and tidal things happening because Jupiter just makes it go nuts. It's close to Jupiter, so it's under that big gravitation, and it has a lot of things going on in Io. Not as much of that happens in Europa, Ganymede, and Callisto. But again, if you're interested in the moons, we talked about that too in a previous live. But here's the pretty pictures. Okay, and then, oh, let's look at this. Uranus and Neptune are decidedly blue. Here's the pictures for that. You can see Earth right there as a comparison below. Those are, this is Uranus and this is Neptune, and that's the Earth. Okay, bluish looking planets. Okay, so after looking at all these pretty pictures, we will keep on going to the interesting facts about planets. So this chapter is called Solar System in Perspective. So after we covered a bunch of stuff about the planets, it's almost like worth looking at a summary of everything and like what are the most interesting standout sort of facts that we covered about our own solar system, and that's what we'll do here right now. So once again, thank you for being here. Welcome to the live. If you could please like the live, that would be great. Let me actually share it again. Let me share the live again. If you wanna, their food is falling. If you wanna share anything in the comments about any planets facts, feel free. If not, I'll keep going and we will cover these topics. Okay, so some of the interesting facts I kind of mentioned in the live already, but we will cover it in a bit more organized manner. And actually, the exciting thing about this chapter is that it leads us into exoplanets. So one thing to keep in mind is that understanding our planets in the solar system, for our solar system, is important because it gives us an opportunity to look at quite a few different types of planets. Our own solar system has these 8 planets because, you know, Pluto is a dwarf planet, so we don't count it as a planet anymore. But, you know, the long story short is that, hey, Doro, hello. The long story short is that it does give us an opportunity to look at a variety of planets and whatnot, and gives us sort of an insight into what could be potential other types of planets in completely other star systems, and would they be good at hosting life or not. So part of the big sort of when people ask here as well about the planets or about alien life especially. So one way to approach, are there aliens out there? Are there extraterrestrial life out there? Is to basically pursue this question about exoplanets and understanding the diversity of planets and how many different types of planets there can be and what types of systems they might be in, what properties are affected by what things, like for example our planets, because they're at different distances from the sun, how they condensated, how they formed, everything is affected by that, and then more things are affected by all the different composition, etc., etc. So there is quite a bit to glean from just our own solar system, and that itself leads us to exoplanets, which is, by the way, the main sort of approach to finding alien life, if you're interested in that, you know, in case. So Dora is saying, James, what's up? Just chilling out. Okay. All right, so our aim in studying planets in the solar system, aside from the intrinsic thrill of exploring new worlds, because that's what they are, the planets in our solar system are all different worlds. It's like we say, oh, all the things in this world, well, we just are on one world, which is the Earth. All the other planets are all different worlds and have their own different things going on. But so as much as it's interesting to learn about these other worlds, but also the planets actually give us a huge insight into how our solar system formed and how it has evolved with time. So with enough studying of our own solar system and of our own planets, it also gives us insight potentially into other star systems and what type of planets those might be hosting. or what might be possible there depending on what we think about sort of the temperatures and distances and things like that. And that would give us something to kind of pursue in terms of, yeah, in terms of life elsewhere. This is the Star Trek type of stuff I live for. Yes, absolutely. So one thing I'll say is just prepare yourself, because we're going to cover a lot of exciting stuff on the channel today and for the next few days, because we will absolutely get into exoplanets. And exoplanets are, of course, a huge approach into learning about other life, or like just finding if there is life outside of Earth and seeing if there are aliens and things like that. Because basically, obviously, right? If there is planets that we think could host life, then that's a big lead. Of course, exoplanets are going to be far away, because I talked about it, I think, yesterday's live. Even the nearest star, you should have a huge audience this week. Snow everywhere. Oh, nice. Yes, hopefully. Yeah, no, that's fine. That's fine. Yeah, there is a lot of snow here in Boston tonight, and maybe like all day tomorrow it could keep on being a snow day or something. Oh, that's right. I'm in Belgium. That's right. And I heard that other places are gonna get snow too. So as you said, yeah, maybe there will be more more people coming to the lives because of snow days. Yeah. Absolutely. So basically, we will be getting into exoplanets soon here. It might not happen tonight, but I think over the next couple of days, tomorrow, Tuesday, we will cover, oh my God, excuse me, we will cover exoplanets, and also just prepare yourselves to be a little shocked, because if you thought that the Earth was kind of special, you will see how even our star system, even our own solar system, might be a little special, in the sense that when we looked for exoplanets, there were some sort of shocking results, actually. So again, we should be thankful to learn. We should be thankful to learn. It is very special. Indeed, it is very special. But it might be even more special than we thought, is the sort of confusing thing that we might find sometimes when we study exoplanets. But basically, checking in. Oh, good. Hi, Ben. Hi, Ben. So, prepare yourself for some interesting facts with that as well. And basically this comparative, so the authors call this a comparative planetology. Not, again, I'm learning too right here with you about this, and comparing and contrasting the properties of objects within the solar system. This is very important to do that, because as I said, it comes in handy when we think about exoplanets, okay? Which exoplanets are super important, of course, for aliens. So, our aim in studying planets in the solar system, aside from the intrinsic thrill of exploring new worlds, is to understand how the solar system was formed and how it has evolved with time. We have approached this problem through comparative planetology, comparing and contrasting the properties of objects within the solar system. So we kind of saw how we did that. We were comparing and contrasting the planets. In addition, recent advances have permitted astronomers to detect planets around stars other than the sun. So this is where we will talk about exoplanets. The properties of these extrasolar planets, or exoplanets, as they are called. So extrasolar planets, other stars, planets, or exoplanets as they're called, can be compared and contrasted with the properties of planets within our own solar system. This new information enables us to address the broader questions of how planetary systems in general are formed and how they evolve with time. So these exoplanets are, of course, interesting for other reasons too, but as I said, they're extremely interesting for the alien life reason as well. Because pretty much if we think that there is not life in this solar system other than on Earth. I mean, there could be on Europa, there could be on some of the other sites of this solar system still. So it's not like we've exhausted all the possibilities and research within our own solar system. But of course, the question of is there life outside of Earth is beyond our solar system. It's interesting to consider what would happen or what type of sites are provided by planets in completely different star systems. So that's what exoplanets are. But first, we will continue with our comparative planetology within our own solar system. And keep in mind about some of these features that we learn about too, because remember that when we look at exoplanets, some of the things that we know about our own planets is how we compare and realize, oh, so that exoplanet is kind of like Jupiter, or that exoplanet is kind of like a different planet. You will see how Jupiter is gonna come up, and it's gonna be important to understand some of these differences even within our own solar system. Okay. Reese says, hello, hello. How are you doing? I thought you were sick. I'm glad you're here. The mods are here now. I've been dealing with some weird people, new weird people, that is. So lesson 1, surfaces of planets are shaped by competing internal mechanisms and external mechanisms. So surfaces of planets are shaped by competing internal mechanisms and external mechanisms. The primary internal mechanisms are volcanism, so volcanoes, and in the case of Earth, plate tectonics. So plate tectonics is not something that we see on every planet, okay? We're kind of special on Earth where plate tectonics happen and we get earthquakes and things like that. But volcanism, having volcanoes which can, as you know, cover up impact craters and things like that, is actually quite common. There are other sites in our solar system that are even more active when it comes to volcanoes, okay? The primary external mechanism is impact cratering due to bombardment. So I was about to say something on that, but it's the next thing. We expect that the internal mechanisms will be more important for the larger bodies since these will retain their internal heat longer and thus remain geologically active for longer periods of time. Among the terrestrial planets, this is indeed correct. The larger planets, Venus and Earth, have surfaces on which volcanism and erosion have all but obliterated the evidence of the early bombardment era. So we had an era of heavy bombardment. We call it an era of heavy bombardment in our solar system, which created a lot of impact craters on many of the objects in our solar system, including our moon. But we see a lot less of these on Earth and Venus because things like volcanoes have produced, material and lava that kind of covered up these craters and gave this external feature, basically reshaped the surface so that we don't find as many impact craters. But if you don't have a lot of volcanism happening, a lot of volcanoes happening, in other words, then you will be your impact craters will be still around and much more of a feature on the surface. So we see that being a difference, basically, and depending on whether you have a lot of volcanoes or not, you will have more or less impact craters. So among the terrestrial planets, this is indeed correct. The larger planets, Venus and the Earth, have surfaces on which volcanism and erosion have all but obliterated the evidence of the early bombardment era. The smallest planet, Mercury, has surface features that are primarily the result of bombardment early in the history of the solar system with little modification by volcanism and erosion. So basically, everybody was impacted by the impact craters, probably. These were smaller bodies and planetesimals while we were still kind of evolving, basically. Hitting us and making these impact craters. So, but if you had a bunch of volcanoes and erosion, surface erosion, then your surface will get new features, more updated features, and the impact craters basically get covered up or paved over. So we see less of the crater stuff on Earth and Venus because these are the largest planets in the rocky metallic terrestrial planet category in our solar system. And these have more of that internal mechanism and volcano stuff happening. Whereas Mercury is the smallest one. It had little modification by volcanism and erosion, and Mars is the intermediate case. So Mars is a lot smaller than Earth and Venus, but bigger than Mercury. But Mars is the intermediate case here with ample cratering in some locations and large volcanoes in other locations. So Mars is almost like this intermediate mid planet, which has both lots of, lots of cratering in some locations and also large volcanoes in other locations. Moreover, there's ample evidence for past erosion by water and current erosion by wind. So Mars also, we talked about Mars in detail in one of the live streams earlier, that excitingly, Mars, of course, had the sort of leftover evidence of water, which, that means that might have been something on Mars earlier. But yeah, there is past evidence of past erosion by water and current erosion by wind on Mars. So Mars is another very interesting planet indeed, and especially because it does not have the poisonous atmosphere, and it is a rocky planet. It's a lot like Earth in that sense. Less similar in size and mass, but there's a lot of other redeeming qualities, which is probably why people are trying to go to Mars. Okay, so lesson number 2 about this planetology stuff is more massive, colder planets are better able to retain atmospheres. So that makes sense. Basically, if you are more massive because of gravitation, you're going to retain atmosphere. And also, if you are colder, that probably means colder as in you're farther away from the sun or a star. That probably means that your stuff is not just like going away constantly, like you can retain some of that stuff instead of constantly losing it. So whether or not a body can retain an atmosphere and the chemical composition of the atmosphere it does retain depends on the competition between atmospheric temperature and gravity. More massive planets, all other things being equal, have higher escape speeds and are better able to retain an atmosphere. So this is the gravity thing. If you have more gravity, if you have more mass, then you will have a higher escape velocity of something to, be able to escape your gravity. So bigger planets, more massive planets, all other things being equal, have higher escape speeds. You need to be going a lot faster, or it's going to be more difficult to escape the gravitation of that planet. At a given temperature, the lightest atmospheric particles are moving most rapidly and are the most easily lost to space. In order of increasing mass, consider an array of objects within the solar system. So again, at a given temperature, if the temperatures are constant, then the lightest atmospheric particles are moving most rapidly and are most easily lost to space. So say something happens, and there's sort of an eruption of a volcano or something, and it will spew stuff out. Well, the lightest, let's just say as an example, the lightest parts of the atmosphere could get a pretty high velocity and kind of leave that planet and go out into space, right? So that's why we could lose these lighter materials to space and not have it attached to the planet anymore in the form of its atmosphere. So that sort of stuff also affects things. And of course, if it's very hot, then the molecules will move faster and leave the atmosphere, like sort of an evaporation almost of the atmosphere out to space, basically. Okay, so now we will look at in order of increasing mass. So going from smaller to bigger mass, we will look at an array of objects within the solar system to compare sort of the massive and temperature stuff and how that affects things in terms of atmosphere. Okay, so Pluto, it's a dwarf planet, but we consider it here because it's a lot of people's favorite planet, turns out. Pluto is extremely cold. So as you know, Pluto is very far from the sun. So of course it's cold. Its temperature is around 50 Kelvin. Surface temperature is around 50 Kelvin at perihelion. So when it's closest to the sun, its temperature is still very low, 50 Kelvin. But it is too low in mass to retain anything other than a thin methane atmosphere. So if it had a ton of, if there were things that it could have retained, hi Mad Hatter, that it might have retained those things, but it's too low in mass. Its gravitation is too weak, so it does not retain anything other than a thin methane atmosphere. So it's both of those things at play here. Next, we consider the moon, our moon. The moon is more massive than Pluto. So for all those people for whom Pluto is very important, our own moon is more massive than Pluto. But it is too hot. It has a temperature of around 350 kelvins at the subsolar point to retain any atmosphere at all. So it's more massive, but not massive enough in terms of how hot it is to retain any atmosphere. So it's complicated, but we'll get through it. Next is Mercury. Mercury is too low in mass and too hot to retain an atmosphere, aside from transient solar wind particles and atoms sputtered from its surface. So it might have something like transient atmosphere because it's so close to the sun, so it gets affected by the solar winds and things like that, but it's going to be very transient. It's too low in mass, not enough gravitation, and it's too hot because it's very close to the sun. Mars is cool. It has a surface temperature of 290 kelvins on a warm summer day. So a warm summer day of Mars is around 290 kelvins, but its mass is too small for it to retain anything more than a weak carbon dioxide atmosphere. So too bad. That is the thing that I mentioned earlier, that the planet that is more close to our size is actually Venus. Mars is quite a bit smaller, so unfortunate because Mars is the one, that is better in other ways. But yeah, Mars is cool, 290 kelvins, not bad. But it's maybe a little too cold, but it's not terribly cold, right? Not as cold as Pluto, but its mass is too small for it to retain anything more than a weak carbon dioxide atmosphere. And then we come to Venus, my favorite. It's too hot. It has a temperature of 740 Kelvin. That's so high, so hot, but it's massive enough to retain a thick carbon dioxide atmosphere. So see how I was mentioning earlier about the carbon dioxide, too much carbon dioxide in the Venusian atmosphere. I love that word, Venusian. Too much carbon dioxide in the Venusian atmosphere, but it does have a thick atmosphere. So it's almost like Venus was so close. It has an atmosphere, which is actually very helpful, but it's too hot because it's closer to the sun. And that heat also doesn't let it have oceans. And so those oceans, the absence of those oceans makes it so that it has too much carbon dioxide because the water is not absorbing it and turning it into limestone like we do on our excellent planet Earth. So Venus, too hot. Plus, I think Venus is too hot too. Like, it's almost like you can make yourself maybe warmer, but I don't know if you can make yourself cooler on such an extreme sort of environment, right? In such an extreme sort of environment, like the Venusian surface being 740 Kelvin, that's quite a bit high, you know, and also the very thick poisonous atmosphere, which is mainly carbon dioxide, which is kind of bad for us. But I mean, there could be other things that like that. I don't know. The Earth is warmer than Mars, but it is massive enough to have retained a dense carbon dioxide atmosphere initially. So we also did that. This evolved into a thinner nitrogen and oxygen atmosphere because of the presence of liquid water, like I was saying, which removed the carbon dioxide, and plant life, which added the oxygen. So we have oceans and plants to thank when it comes to our own home planet being habitable and good for us, where we can breathe and stuff. Who do you think created the pyramids? Doro did, apparently. He did. So anyway, the Earth is warmer than Mars, but because it has liquid water, it's both massive enough to have retained a dense carbon dioxide atmosphere initially, but this evolved into nitrogen and oxygen atmosphere because of the presence of liquid water, which turned the carbon dioxide into limestone, like I was saying. And then plant life also helped to convert carbon dioxide to oxygen. So we have oceans and plants to thank, indeed. Ooh, can we get 20 likes? This channel used to be about the moon. Not really. It can be again. We actually just talked about the moon. You missed it. We did land on the moon. Has missed the moon point. Oh yeah. Can you please like the live? Thank you so much. Could we get 20 likes? So, that was about the Earth. Next is Jupiter, or sorry, the Jovian planets. The Jovian planets are sufficiently cold and massive to retain thick atmospheres of hydrogen and helium. So it's very interesting when you go over to the Jovian planets, Jupiter, Saturn, Uranus, and Neptune. All of those are, of course, extremely massive compared to the terrestrial planets. So all of them are sufficiently cold. In fact, they will have stuff that will condensate at lower temperatures, right? Because they're farther away from the sun. But also, yeah, in general, they're sufficiently cold and massive to retain thick atmospheres of hydrogen and helium. Yay! Thank you so much. Yes, please. Thank you so much, Mad Hatter, for liking the live. Everybody, please like the live. And if we could get 20 likes, that'd be great. So that was about the massive, more massive, colder planets are better able to retain atmosphere. So that was about atmospheres and how the mass of the planet and the temperature of it plays a role. Next, we will talk about the giant satellites of Jovian planets show patterns consistent with our idea about formation of the planets. So the Jovian planets, yes, this is ginger ale. The Jovian, it's ginger ale mixed with lemon. This thing has a lemon in it. So I'm drinking ginger ale with squeezed lemon juice. In fact, I poke and prod the lemon with this thing to release more lemon juice into the ginger ale. It's amazing. Thank you. Thank you so much. Please do like the live and share the live. Isn't it Trump POTUS Day today? On Monday, yeah. Actually, Doro, we have Monday off, right? Tomorrow's off for people. That could be why some people are able to stay on the lab. Yes, Reese. Happy Monday to you. Reese says it's already Monday here in Belgium. Happy Monday. Doro says, sadly, I'm not off. It's actually a travel day for me. Very nice. He gets paid $1 million daily. The Jovian planets are sufficiently cold and massive. Nice. Okay. So speaking of Jovian planets, our next point is going to be about the moons. So the moons of the Jovian... You're rich, not me. You seem sad. Do I seem sad? I don't think I'm sad. Giant satellites of Jovian planets show patterns consistent with our ideas about formation of the planets. The satellite systems surrounding the Jovian planets formed in a process. Ooh, that's right. So basically, it's really interesting because we kind of know we have ideas for how our solar system formed with the the condensates happening, the planetesimals forming and all that. But it's almost like, as you know, the Jupiter and its Galilean moons is kind of like a mini solar system of its own. So it's almost like these bigger planets like Jupiter, Saturn, etc. give us a way to look at what happens in a sort of more mini solar system, because those planets and their moons are almost like their own little solar system. So that's what we're talking about here. So the satellite systems surrounding the Jovian planets formed in a process that mirrored that of the solar system as a whole, with a central massive warm object surrounded by an orbiting disk of material. I was going to say orbit disk, but no. So basically Jupiter, for example, actually outputs a lot of heat. We talked about that, like the reasons for that and all of that stuff. So it's very interesting. Jupiter is like a little sun who has a bunch of like satellites, which are kind of like its planets, right? So Jupiter is a planet, and so the satellites are its moons, but you get the idea. Jupiter basically gives us a way to almost study another little mini solar system. Thank you for being here, and please do like the live, guys. Thank you. Welcome to the live, and thank you for being here. So, the satellite system surrounding the Jovian planets formed in a process that mirrored that of the solar system as a whole, with a central massive warm object surrounded by an orbiting disk of material. The inner satellites of Jovian planets Io and Europa, for example, formed under relatively warmer conditions than the outer satellites, such as Ganymede and Callisto, for instance. The higher densities of the inner satellites imply a higher fraction of dense refractory rock and a lower fraction of low-density volatile ice. Inner satellites show evidence of volcanism driven by tidal heating in this case and resurfacing. In the solar system, the larger planets Jupiter and Saturn formed in the middle of the system where there was a favorable trade-off between temperature cool enough for volatiles to condense and density high enough to make massive bodies. Similarly, in the satellite systems of the Jovian planets, the largest satellites formed in the middle of the system. Jupiter's Ganymede, Saturn's Titan, and Uranus's Titania are the largest satellites. So it's so interesting. Just like the sun's most massive planets are Jupiter and Saturn, right? And they're sort of in the middle of the solar system-ish. So they're super massive. So it's like basically they're cool enough for the volatile stuff to condense and make the planets, and they're high enough to make massive bodies. So there's this trade-off between temperature and density, which let Jupiter and Saturn be the way they are. And the same thing is kind of true for the moons of these planets, such as Ganymede is the biggest satellite, just period, in the solar system. It's a moon of Jupiter, and it's also the biggest moon. Like, it's a giant moon. It's one of the giant moons, and it is a moon of Jupiter. So, and Ganymede is not the closest satellite of Jupiter. Remember, the closest Galilean satellite of Jupiter is Io, then Europa, then Ganymede. So actually, Io and Europa, especially Io, has a ton of volcanoes happening, a lot of volcanism, a lot of tidal heating, tidal type of features, whereas Europa has less of that, and Ganymede and Callisto pretty much don't. So even the satellites of Jupiter have so much diversity depending on their distance from Jupiter, which is a warm body, a warm, massive body, and outputting heat. So that also gives us a great look at how things would have developed in our own solar system. Condense. Yes. So let's read that part again. The higher densities of the inner satellites imply a higher fraction of dense refractory rock and a lower fraction. So that's the other thing. Like, the closer planets or the closer satellites will be higher density, because if they formed something, that means that that material condenses at a higher temperature. So it's not going to be some ice or something that will be too volatile and, evaporate away at a higher temperature. So it's so interesting how the devil is always in the detail with these things, like the closeness, the temperature, the mass, all of that matters so much. So the higher densities of the inner satellites imply a higher fraction of dense refractory rock and a lower fraction of low density volatile ice. Lower fraction of low density volatile ice. Remember, the stuff that would evaporate away. Right. And then inner satellites show evidence, of course, of volcanism driven by tidal heating in this case and resurfacing. And of course, the inner satellites show evidence of volcanism because Jupiter is closer to the inner satellites. So it's affecting the inner satellites and producing those the internal tides. Like, literally, Jupiter is like creating tides on the insides of these planets. So it's no joke to be close to Jupiter, right? Jupiter is huge. And so just like even our moon, which is smaller than us, causes tides on our Earth, on our oceans, right? Same thing, Jupiter being so crazy big is going to produce tides even on the internal material of Io. So being close to Jupiter is like a completely different lifestyle. It's not the same environment as being, say, at a bigger distance from Jupiter, and so on and so forth. Like for the various Galilean moons, they're at different distances. Io is first, then Europa, then Ganymede. and then Callisto, and the things are completely their structures and what they are completely different. As a PhD in physics, I commend you. Incredible achievement. Oh, thank you. I do have a PhD in physics. She has a PhD in pain. Okay, everybody, thank you so much for being here, and please like the live. I want to get to 20 likes, please. All right, so next, oh yeah, let me finish off this. In the solar system, the largest planets, Jupiter and Saturn, formed in the middle of the system, where there was a favorable trade-off between temperature cool enough for volatiles to condense and density high enough to make massive bodies. So Jupiter and Saturn, the most massive planets of the solar system, are sort of in the middle-ish of the solar system. Similarly, in the satellite systems of the Jovian planets, the largest satellites formed in the middle of the system. Jupiter's Ganymede is the largest one, sort of in the middle of the system. Saturn's Titan is the largest one for Saturn, also one of the giant moons, sort of in the middle of the system. And then Uranus's Titania, which is also in the middle of the system, okay? So lots of things to understand and learn from even the satellites of these bigger planets, because they give us entire systems to understand, and almost like mini little solar systems of their own, if you will, and gives us an opportunity to understand how our own solar system evolved and whatnot. Thank you, Mad Hatter, for being here. Thank you, everybody, for being here. We should do fun science quizzes sometimes on here. Okay. I do ask science questions sometimes when you guys are fighting amongst yourselves. If you're interested, we can have more of those. Can we please get 20 likes? I will keep going. Kind of want to get through the material a little bit more before we shoot the shit, okay? All right, lesson 4. Many unusual features of the solar system can be attributed to giant impacts. Oh, this is Reese's favorite topic. Pop quiz. Okay, Reese, tell us, why are there impact craters on the moon? Thank you so much for liking the live. Please, let's get 20 likes. It is only within the last few decades that astronomers have realized that some of the more unusual properties of solar system bodies can best be explained by giant impacts that occurred relatively late in the formation of the solar system. Giant impacts seem to be the best way to account for the relatively large satellites of small planets. So giant impacts seem to be the best way to account for the relatively large satellites of small planets. In the case of Earth-Moon system, the non-equatorial orbit of the moon and the differences in surface composition between the Earth and the moon suggest that the histories of these objects are quite different. That's right. We saw that the surface composition, remember, of Earth was more diverse. There were more things in our surface and less things in the moon's surface. And also, the moon does not have iron. It does not have an iron core like we do. So, 6 watchers, 20 likes, Mission Impossible. I mean, the number of watchers is constantly changing. So, you know. Yay! Oh, very usually when you have a large surface, something small hitting it will think it's flat. You know how there are people who think that the Earth is flat? It's because their experience of the Earth is flat. So some of that might also explain our earlier impact crater discussion. You're here all week. Yay! Wow! Okay, so remember how we spoke about this already, but it was actually very, very interesting that even, see, this is the interesting thing. This is the amazing thing, I would rather say, about even, about the solar system, but even our own Earth and Moon have more diversity than one might think. So we covered sort of the various different possibilities or theories about how our moon itself was formed. But pretty much the interesting thing is that our moon is very different from our Earth. And it's kind of like even that particular point or diversity or history is something to be very excited about, and it's so very interesting. There's so much diversity, so much to learn. So as much as the exoplanets are interesting and thrilling new work, it's also the case that our own solar system has a lot of diversity and variety in terms of its planets and the various moons and satellites. So Grimmy, don't you have work tomorrow? So let me read this again. Giant impacts seem to be the best way to account for the relatively large satellites of small planets, of small planets. In the case of the Earth-Moon system, the non-equatorial orbit of the Moon and the difference in surface composition between the Earth and the Moon suggests that the histories of these objects are quite different. So we spoke about the various theories already, but let's keep going here. A giant impact between the Earth and a Mars-sized planetoid. Wow, a giant impact between the Earth and a Mars-sized planetoid seems the best way to account for the current Earth-Moon system. So good, we're covering it again. Basically, we saw that one of the theories was that basically some Mars-sized planetoid collided with Earth and further contributed to the iron core of the Earth, and the part that got ejected out was more from the surface of the Earth, and that later on became the moon of the Earth, and it did not inherit the Earth's iron core and some of the Earth's overall surface diversity. So the moon is sort of a more simple system and does not have all the different materials that we have on Earth, and it's less dense as well. But it's not like it's the least dense thing in the solar system. There are definitely moons that are less dense, such as actually some of the Galilean moons that are farther away from Jupiter. So our moon is not like, it's still rocky. So it's still a very interesting moon. And it is actually one of the giant moons, one of the 7 giant moons of the solar system. So again, it is a very interesting moon, but because of its differences with Earth, it's actually kind of sort of something to think about how it might have formed, and this is the best guess we have. No, several different things. So remember the moon's composition is very different from the Earth. So if it came only from the Earth, like in a sort of more straightforward way, then it should have inherited more properties of the Earth. More materials would be sort of same as the Earth. Earth has a ton of iron, moon has like none. So that's one difference. Another difference, it's a non-equatorial orbit. So the moon, the Earth-Moon system, within the Earth-Moon system, the non-equatorial orbit of the moon is another reason why we think it's not such an obvious way in which it formed. And the main thing, like I said, was the surface composition. The surface composition between the Earth and the moon suggest the differences in the surface composition suggest that our histories, how we formed versus how the moon formed, are sort of two different things. Our histories are not completely the same. It's not like us and the moon have been together forever. That's what that means. Wow, okay, I will do, I think I'll Uber there. How sustainable is life on the moon? Well, the moon doesn't have any atmosphere, so that kind of sucks. It could be something. Why not? It's close. We could definitely have a colony on the moon. I think we pretty much already do. We can live there now, head on up there. Okay, we'll do. I think I'll Uber there. Actually, I remember when we were in college, we talked about going to the moon. That was something. We can and will live on the moon. But yeah, the moon doesn't have an atmosphere, but it's not bad. I think the moon is kind of similar, like because it's made of a part of the Earth's surface. In a lot of ways, it's similar. It's gonna feel like, I think it's gonna feel like here-ish, just less gravity. So not a bad place, and it's very close. So why not? You know. But yeah, a giant impact between the Earth and a Mars-sized planetoid seems the best way to account for the current Earth-Moon system. In the case of Neptune's satellite Triton, so we talked about Triton the other day. It was a sad story, actually. In the case of Neptune's satellite Triton, its retrograde motion strongly argues that it is a captured body. The most obvious way of slowing Triton sufficiently for it to be captured by Neptune is to have it collide with a satellite already orbiting that planet. In addition, the retrograde rotation of Venus and the sideways rotation of Uranus is best accounted for by impacts with large bodies that severely altered the orientation of their rotation axes. On bodies with the oldest surfaces, we see clear, direct evidence for major collisions in the impact basins on the Moon, Mercury, and Callisto. Collisions with, and so oldest surfaces means it's not been paved over by volcanoes. Collisions with large objects can have a global impact on a planet's topography, as the Calories Basin on Mercury attests. At the antipodes of the Calories Basin, the surface has been shattered into chaotic terrain by the converging seismic waves set off by the impact. So these impacts really impact the planets and the moons. Mars probably condensated as its own planet around the sun, because if a planet is going around the sun, to go from going around this, basically, yeah, I don't know. I don't know, but I was gonna say that if it's orbiting the sun, to if it weren't already orbiting the sun, that would be kind of hard. I think when these impact type of things happen, the resulting object starts to orbit the parent planet, basically. You know what I mean? In our case, our moon orbiting us is also in a sort of special kind of orbit. It's not equatorial. So we are thinking about all these different ways in which it could have formed. But basically, if something is orbiting the sun, to make it orbit us is not a joke. Yes, I'm excited, I guess. Why do you ask, Birdie? And then if it was part of Earth to then go so far away and then orbit the sun, I don't know. I don't know. I think somebody asked about the. Let me address something else real quick here. So. Rebound. We covered this either. I'm like trying to say a sentence and I'm reading your comment at the same time. We covered this already, but I wanted to say something. There's one more thing in which. Oh yeah, so that's the heavy bombardment. And where does it talk about? Oh, you're asking about, am I excited for Trump? Oh, you're talking about the president change tomorrow. Epic opening statement. Okay, I forgot. Ooh, we got 22 likes. Thank you so much. Can we get 25? Can we get 25 likes this time? I'm trying to look something up about the moon as we speak. So give me a second. I think maybe we're good. Here, let me read real quick. So the six Apollo missions that successfully landed on the surface of the moon returned a total of 400 kilograms of surface rocks from both Maria and Highland. So this is our own moon. Real quick, we've covered it in the past, but here it is again. After study, lunar rocks were discovered to differ from terrestrial rocks in several fundamental respects. All lunar rocks are igneous, solidified lava. There are no sedimentary rocks made of weathered bits of rock cemented together, or metamorphic rocks made from igneous or sedimentary rocks subjected to high temperature and pressure. Lunar rocks do not contain detectable amounts of water. By contrast, Earth rocks can contain as much as 3% water and nearly always contain detectable amounts of water. The iron in lunar rocks is not oxidized. Iron reacts quickly with free oxygen to form ferric oxide, Fe2O3, otherwise known as rust. This indicates that the lunar rocks have never been exposed to an oxygen atmosphere. So maybe this stuff happened before we had substantial oxygen in our atmosphere. Like maybe this moon formation and ejecta of Earth becoming the moon after colliding with a different thing might have happened before we formed an atmosphere with significant oxygen in it. That could be something. This indicates that the lunar rocks have never been exposed. The lunar rocks have never been exposed to an oxygen atmosphere. Lunar rocks are depleted in volatile elements. This suggests that the rocks of the lunar crust were exposed at some point to higher temperatures than were the rocks of the Earth's crust. The higher temperatures would also explain the lack of water in the lunar crust, which was boiled away. So there's also no water on the moon, whereas there's water here. So, you know, lots of little facts, interesting facts and clues to kind of help us form a picture of what might have happened to give us this moon. Only the moon was given to us, right? Hi, Fuji Baba, Shono Mono. Ooh. Here it is. Here it is, the thing I was thinking of. I think somebody asked about the magnetic field on the moon, maybe, if I saw that. There's a bunch of nonsense in the chat, so I can't always read the relevant information. Thanks to these dumb people who don't know English. Where was it? How sustainable is life on the moon? That's a joke, the English part. Maybe Mars and Earth were the same. I don't know. Is it in a polar... Where was it? Somebody asked about the magnetic field on the moon, or are we... am I imagining that? Okay, so let's read this part. The Earth's moon has an average density of around 3370 kilograms per meter cubed. So that is less dense than the Earth, but it's more dense than, for example, some of the other giant moons, okay? About the same as the density of the Earth's crust. So the moon is sort of similar to the Earth's crust, whereas the Earth, of course, has a core of iron and everything. It's much more dense and it has more layers. Because of the moon's small size, it has cooled more rapidly than the Earth, leaving it nearly dead, geologically speaking. So what do we mean by geologically speaking nearly dead? As in volcanoes are not happening and all this stuff is not happening. And again, that's why we see the impact craters on our moon, because if it had made volcanoes, that the impact craters would have gotten paved. But instead, the original impact craters are visible because nothing has gone over it. Nothing has paved over it. So moonquakes are rare and weak. As you know, earthquakes are pretty common. Moonquakes are rare and weak. However, seismic instruments left at the Apollo landing sites were able to record artificial moonquakes generated by discarded Apollo ascent stages and Saturn V third stages crashing onto the surface, and by explosive charges set by astronauts. So they were able to make artificial moonquakes, maybe to see whether their instrument is sensitive enough to pick up on moonquakes, because say if you have an instrument, and you want to make sure that it can actually pick up on moonquakes, you might want to calibrate it with artificial moonquakes, because otherwise you're like, oh, is this instrument even working? So that's the significance of that, okay? So once they did all that, from the analysis of the seismological data, it is known that the moon has a solid core of density around 3,500 kilograms per meter cubed, a mantle of density around 3,200 kilograms per meter cubed, so a little less dense, and a crust of density around 2,900 kilograms per meter cubed. Unlike the terrestrial planets, the moon does not have an iron core, which would have, unlike the terrestrial planets, the moon does not have an iron core. This is what I was mentioning, which would have a density of around 8,000 kilograms per meter cubed. So it does not have the iron core. Artificial moon quakes, like earthquakes, but moonquakes. So this is where it complicates the comprehension of our history and the moon's history, because we have an iron core, the moon does not. So that's what's going on, you know what I mean? So the seismological data tells us that it has a solid core of density around 3,500 kilograms per meter cubed. So that is a bit more dense, but it's not as dense as our core, which has iron. A mantle of density 3,200 kilograms per meter cubed, and a crust of density 2,900 kilograms per meter cubed. Unlike the terrestrial planets, the moon does not have an iron core, which would have a density of 8,000 kilograms per meter cubed. But it's at least somewhat differentiated. So differentiation is where the heavier stuff sinks to the center. So it does have that, right? But it doesn't have it to the level where we do, because we have an iron core and we have even more diversity in our materials. Because of the lack of a liquid iron core, the lunar magnetic field, so somebody asked about that, is weak. Its magnetic field is around 10 to the 9, 10 to the minus 9. 10 to the 9 would be a lot. Because of the lack of a liquid iron core, the lunar magnetic field is weak, with around 10 to the minus 9 Teslas is the magnetic field on the moon. However, magnetization of surface rocks indicates that the magnetic field was stronger in the past, maybe around 2 times 10 to the minus 6 Tesla, about 3.3 billion years ago. So that's another little tidbit, which is that there's magnetization, so there might have been a more stronger magnetic field at one point. Even to the naked eye, the moon obviously has both darker and lighter regions. The lighter colored regions are seen to be mountainous and heavily cratered when seen through a telescope. So even through a telescope, you can see this. Even through a telescope, you can kind of see the lighter colored, or you know, the cratering on the mountainous regions. So these regions that are mountainous with the craters, those are called lunar highlands. The darker colored regions are smoother and lower lying. Some early telescopic observers thought that the smooth dark regions were oceans, and thus called them maria, or the Latin word for seas. Although the maria have long been shown to be solid rock, the inaccurate name has stuck. In fact, the maria are not perfectly smooth. They do have a few scattered craters on their surface. You know, they aren't nearly as cratered as the heavily pocked highlands. However, the maria are concentrated on the side of the moon facing the earth. So, that's the darker spots, right? The smooth, dark regions people thought were oceans. So like people say, oh, there are flaws on the moon or something like that. There are darker spots on the moon. That's the Marias. So, and most of those, the Maria are concentrated on the side of the moon facing the earth, which is interesting. You know, we see some of those darker spots easily through the naked eye. The lunar highlands are an old surface. So the lunar highlands are an old surface, largely unchanged since the time of heavy bombardment with planetesimals. So I was saying how, you know, the heavy bombardment period was pretty old. So if you're seeing these original impact craters, that would also indicate a older surface since the time of the heavy bombardment with planetesimals. The highland surface is saturated with craters. That is, there's no part of the surface that doesn't lie within a crater. The ages of igneous rocks, either lunar or terrestrial origin, can be determined by the process of radioactive dating. So, you know, radioactive dating of rock samples brought back by the Apollo astronauts revealed that the typical age of a highland rock, that is the time since it solidified from lava, is 4 billion years. The typical age of a Maria rock is around 3.5 billion years, the ages of moon rocks are in marked contrast to the measured ages of surface rocks on Earth, which show a wide range of ages. So we have, again, more diversity in our ages of the rocks on Earth, which the moon seemed to be not like that. The moon seems to be more sort of homogeneous in that sense. Wow. So very different. Even our moon is quite a bit different from us. I love how much you love physics. Admirable. Thank you. Autistic core. Bedtime for me. So that was a little bit about the moon again for you guys as we are covering some interesting facts about the planet stuff. So we're basically covering comparative planetology within the solar system. And because some of the moon stuff came up, I thought I'll go back over our own moon here with you a little bit so that you know how it has some special features of its own, which is kind of different even from us, from the Earth and such. Okay, so giant impact between the Earth and a Mars-sized planetoid seems the best way to account for the current Earth-Moon system. Yeah, where they thought there was an impact, the planetoid gave us more material and merged with us, in fact, contributed to our iron core, and it ejected out material more from the crust and gave us the moon, which later became the moon. So very interesting. I'm quite intrigued by this, actually. Ooh, and I have some pretty pictures here that I'm going to show you as well. So quick. Interviews with NASA astronauts who state that you can see stars from space. Okay. Origin of the solar system. So next I want to keep going and talk about our understanding of the history and evolution of the solar system and where things might still be kind of incomplete and intriguing and interesting. This whole chapter is kind of really interesting. It tells us certain things that help us with our insights and especially prepares us for exoplanet discussion. But it also leaves us with some questions. And so it's good to think about those things, and it's good to do your own research on those things and work on such problems if you wish. So our understanding of the history and evolution of the solar system is still incomplete, but a comprehensive, self-consistent picture has begun to emerge. Our mental picture of the solar system forming from a rotating protoplanetary disk, explains many of the basic features of the solar system. Planetary orbits are all in nearly the same plane. So we think that there's this sort of rotating protoplanetary disk of stuff that, the sun, it's all sort of in the same plane. Planetary orbits are all in nearly the same plane. The sun's equator lies close to this plane. Planetary orbits are nearly circular. Planets all orbit in the same direction, Most planets and the sun rotate in the same direction as the planet's orbital motion. Not all planets, but most of them. We have also noted that although the sun contains, so these are really cool. Planetary orbits are all in nearly the same plane. The sun's equator lies close to this plane. Planetary orbits are nearly circular. Planets all orbit in the same direction. Most planets and the sun rotate in the same direction as the planet's orbital motion. We have also noted that although the sun contains 99.8% of the mass in the solar system, it contains less than 5% of the angular momentum. The planets represent the material in the pre-solar nebula. So it all started from this giant gas cloud or nebula of stuff that cooled and condensated to make the sun and the planets, right? So whatever mass and angular momentum was in that is eventually going into all of this stuff. So let's see how that works. So we know that the sun is obviously gigantic in mass compared to the planets. It contains 99.8% of the mass in the solar system, just period. But it contains less than 5% of the angular momentum. The planets represent the material in the pre-solar nebula that had too much angular momentum to contract into the sun as it was forming. Oh my gosh! I love it. So the stuff that was too much angular momentum, that stuff didn't go into. That stuff didn't become the sun. Because the sun is like, I'm gonna be big. It's like that audio. I'm big, I'm brave, I'm beautiful. The sun is like, I'm gonna be a lot of mass, but don't make me move too much. That's so funny. Oh my gosh. I love it. 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 Because, yeah, if you think about it, the small stuff, I mean, there's also asteroids and comets. We haven't talked about that. But that's so crazy. That's so crazy. Do you think the universe will recollapse? Well, it's flat at the moment as far as we know, meaning that two free particles should never meet. Flat means that two free particles in the universe. So this is a cosmology question, by the way. Two free particles, if they meet, then that's a closed geometry of the universe. If they diverge like this, then that's an open geometry of the universe. And if they never meet, they just stay parallel, two free particles, then that's flat. So currently we think that the universe is flat and it's expanding. Right now we're in the era of expansion for sure, to the point where dark energy, the thing that we don't know exactly what it is, but it does cause the universe to expand, is the dominant ingredient of the universe. So currently it doesn't look like it will recollapse, but that I'm just telling you about what we know so far from the history, from the Big Bang to evolution to the current status. We do know, this is a cosmology tidbit, but this is cosmology discussion now, but we do know that the scale factor, right, dependence on time has changed as the makeup of the universe has changed. So the scale factor's dependence on cosmic time is different for when the universe was radiation dominated versus matter dominated versus now, which is dark energy dominated. So this change in itself is a research topic, and you should look into the cosmology models. So the question you asked, there's three there's more details than this, but there are three cosmology models: flat universe, open universe, and closed universe. And basically, as far as those three go, we think it's flat. But as far as whether it will recollapse, well, we know that the universe is expanding and its expansion is accelerating. So, period, the universe is expanding. Like physical distances between faraway objects, far away from each other, is increasing with cosmic time. And the scale factor is a way to measure that, or write that down, etc., etc. And so we also know the scale factor's dependence on time, how the scale factor depends on time itself, is the Hubble rate, all that stuff. So we have some live streams done in the past on this topic. I think recently too I talked about the universe, because every so often I like to talk about the universe. It's the coolest topic, really. But yeah, you should definitely catch those live streams in the past if you have questions and if you want to learn about this topic in more detail. It's also probably one of my more favorite topics, but that's why I'm taking the time right now. But basically, there was the Big Bang, there was radiation-dominated universe. It was a hot, dense, energetic, crazy jungle of mainly photons, electrons, and positrons. There was a neutrino breakup with the cosmic plasma, and there were very little baryons in the early universe. And then we started to evolve more the universe from that Big Bang stage. And the first, there was very little baryons. I hope you understand that. Like, there's very little of the stuff that we are made of, shit like that. And basically, the Big Bang nucleosynthesis made hydrogen and very little helium and trace amounts of lithium. So that means that every element heavier than helium, pretty much also heavier than hydrogen, even a lot of helium is made in the stars. So ultimately, when the stars started forming, the first generation of stars, later stars, etc., that's where the heavier elements were made, and the universe also cooled and expanded. So the expansion is another thing too, which has been a sort of thing that's been happening throughout and affected things as well. And then dark matter is one of the cosmic ingredients. We talked about the 5 cosmic ingredients. They are photons, baryons, dark matter, neutrinos, and dark energy. Those are the 5 cosmic inventory type of things. And we saw that then later on it became matter dominated, and the cosmic the scale factor goes as t to the 2/3 at that point. And then now it is dark energy dominated, where dark energy is 70% of the critical density of the universe, which is critical density meaning all of the stuff's density in the universe in the current time. So basically, yeah, that's the entire history of the universe in like 4 minutes. So that's where we're at. Currently, we have 70% dark energy, 25% dark matter, and like 5% ordinary matter, or the baryons. So we don't know what dark energy is. We don't know what dark matter is, but dark energy evidence is there, and we know that the universe is expanding. So if you ask, this is all to answer that question, is will it recollapse? If you ask if it will recollapse, I would just say, I don't think I know. I don't think the evidence is saying that there is any collapse happening right now. There is more expansion happening right now. The universe is not expanding at the speed of light. Who said that? The universe is expanding, and the expansion of it is accelerating, but there is nothing about the speed of light in that particular topic. Well, at least it's not necessarily expanding at the speed of light. But supernova data, maybe this is where you're getting that from. No. If the universe is no. The supernova data was used to give us evidence of the expansion of the universe. So maybe that's what you're thinking of. The supernova data, basically, it is like light data. Its luminosities of various supernova were used to figure out basically these candles. There are things called candles in astronomy, things of the same absolute magnitude in luminosity that they use to figure out, well, is there any difference in apparent magnitude? And if there is, then it's because of the expansion of the universe. So they used supernova data to prove the expansion of the universe, but there's no the expansion is nothing to do with the speed of light. Speed of light is important in understanding general things, but it's not necessarily the speed of light. Okay. So yeah, it's very interesting indeed. Hubble rate is like pretty much, let me get my other book. Basically, we know oh yeah, I guess you might have been thinking of that. Cosmic microwave background radiation is just the old photons hanging out still from when the universe was around 300,000 years old. So cosmic microwave background radiation is just a bunch of photons which are a relic of the early universe. And if we look back in time by looking far, far away, basically, then then we get measurements of the cosmic microwave background radiation. So it's just a bunch of photons from a certain era of the universe, and it's associated with the early universe. And it has many, it gives us, damn, I woke up to this. Good. It gives us, oh yeah. Oh, my phone is at 1%. I need to charge it. Oh my gosh. Oh my gosh. Oh my gosh. Oh my gosh. It's gonna die any moment now. Exactly. It's like a photograph. It's like a photograph of the universe, really, because back then the photons were very important. The photons were like the main thing. So really, it's like a photo of the universe, pretty much. Ooh, and today, actually, I can show you the cosmic microwave background radiation picture. I found a spot where that is available, explaining the entire history. I thought you said that. Wow, baffling. Thanks, Mad Hatter. Thank you for the question. Thoughts on distant civilizations. Damn, I woke up to this. Yes. Okay, so let me show you a picture now. So I guess we will continue the planets next time because we were at a pretty good point anyways. Pretty much I was just excited that the sun contains 99.8% of the mass in the solar system, but it contains less than 5% of the angular momentum. The planets represent the material in the pre-solar nebula that had too much angular momentum to contract into the sun as it was forming. If we lol, what's your favorite space movie? It's Contact, but she hasn't seen it yet. That's very true. I have not seen Contact yet. How do you know that? I think we talked about it at one point. So let me show you, since you asked about the cosmic microwave background radiation, it's actually incredibly important topic. When we talk about the universe again, we will touch upon it again. But pretty much the cosmic microwave background radiation is like the most, it's one of the most, there's Suji Mama. It's actually one of the most important things that help us, or one of the most important measurements that help us to study the universe. Okay, since you guys asked universe related questions, I was covering planets, but universe is always a cool topic. The entire universe's history and evolution and all that. There are a few different things that really help us with that, and this is one of them, and we will talk about it again and again. But here's the picture for that. So this is a color figure now, temperature fluctuations of the cosmic microwave background after removal of the dipole temperature distortion. So it looks, kind of like this. This is temperature from negative 200 microkelvin to plus 200 microkelvin. And this is a 5-year map of that measurement of the very old photons. So I was asking her favorite movie, Fast and Furious 9. No, that's not my favorite movie. So is the dark part in the middle, that part. Koi Mil Gaya. Oh, it's temperature. Yes, it is. Are you familiar with Ed Witten, brilliant physicist? Yes, I have heard of him. Exactly. Yeah, indeed. Ooh, and also, if everybody could please like the live, that would be great. If we could get 20 likes, or not 20 likes, 30 likes, maybe even 25 likes, that would be great. But yeah, Edward Witten, we have actually mentioned him and talked about some of his work very briefly here, not in a lot of detail. But yeah, so this is the temperature. It's basically the temperature of those photons. It's something like 2.7-ish Kelvin. So actually, I'll let you look at this, and then I'll read to you about the cosmic microwave background radiation a little bit so that we cover this topic at least briefly here today. So keep looking at this picture of the cosmic microwave background radiation measurement, and I'll tell you a little bit more about it. Yes, it is the universe in exactly. Yep. Visible implies like visible wavelength of light, but I think I know what you mean. Like, yeah, no, this is the universe as we see it. This is the sky. It's the sky. So not necessarily visible wavelength only, but I think I know what you mean. So let me tell you a little bit more about the cosmic microwave background radiation because it's very important. We have talked about it already. By the way, the quantity to quantify the change in the scale factor and its relation to the energy, we defined something called the Hubble rate at one point. We talked about the math of this earlier, at least, well, there were several lives on this, but if you look for this particular live stream episode called, I think I named it Einstein's Equations, we definitely talked about this math in more detail. But basically the Hubble rate is dA dt over A, where A is scale factor and T is cosmic time. And so this dA dt over A measures how rapidly the scale factor is changing. And also, for example, if the universe is flat and matter dominated, so that the A or the scale factor goes as T to the 2/3, then the Hubble rate becomes 2/3 T to the -1. And so this is a powerful test of this cosmology to measure separately the Hubble rate today. So if you measure the Hubble rate and you get your answer, it will tell you about sort of the composition of the universe itself, which is really powerful. So stuff like this too we have covered in past episodes, but let me talk about the cosmic microwave background radiation since you asked about it. So as you can see it looks kind of, you know, it looks sort of homogeneous-y type, like sort of same in every direction. We will delve more into that, but here's an introduction on the on the cosmic microwave background. So the cosmic microwave background offers us a look at the universe when it was only 300,000 years old. So this is very old stuff. So it's very special in that sense. The photons in the cosmic microwave background last scattered off of electrons at a redshift of 1100. Since then, they have traveled freely through space. So they're carrying information from a very primordial time, if you will. They are when we observe them today, they literally come from the earliest moments of time. They are therefore the most powerful probes of the early universe. We will spend an inordinate amount of time working through the details of what happened before the epoch of last scattering, and also developing the mathematics of the free streaming process since then. A crucial fact about this history, though, is that the collisions with electrons before last scattering ensured that the photons were in equilibrium. That is, they should have a black body spectrum. So this is the black body spectrum, basically, and let me see if I can kind of summarize this part. The detection, so this is a 3-ish Kelvin temperature that we have detected, and we have been told that the detection of the 3 Kelvin background by Penzias and Wilson. So by the way, this measurement of the cosmic microwave background radiation that you're seeing it's been measured by many people over the years, and so, you know, it might vary a little bit. Sometimes you might hear 3 Kelvin as the temperature, sometimes 2.7, so just bear that in mind. But basically, the detection of the 3 Kelvin background by Penzias and Wilson in the mid-1960s was sufficient evidence to decide the controversy in favor of the Big Bang over the steady-state universe. So there was some controversy apparently back then. Penzias and Wilson, though, measured the radiation at just one wavelength. So that's another thing. Whether you measure this radiation at a single wavelength or multiple wavelengths, all that stuff, all those details will impact your final result. So let's just keep going here. If even their one wavelength result was enough to tip the scales, the current data depicted should send skeptics from the pages of physics journals to the far reaches of radical internet chat groups, lol. The most important fact we learned from our first 25 years of surveying the CMB. So literally the CMB, this thing you're looking at, has been studied for over 25 years now. It's a very well studied thing, but what they mostly saw, importantly, was that the early universe was very smooth. No anisotropies were detected in the CMB. This period, while undoubtedly frustrating for observers searching for anisotropies, solidified the view of a smooth Big Bang. So we're now moving on. We have discovered anisotropies in the CMB, indicating that the early universe was not completely smooth. So basically, it was smooth at a certain order, but then there are higher order perturbations in this CMB that we will actually look into later on, and those will tell us about certain other more details about the universe, and those are going to be important. So that's one thing. Let me find. Let me find. Another little part of this. Trying to see if there's another good little part that can be used for this introduction. So wow. I'm getting sleepy now. Let's see. I'm still looking for something, so give me a moment. Give me a second. Give me a second. So what is meant by smooth is, so first of all, it's smooth at a certain level, but then there are actually anisotropies that will become important. But when people talk about the smooth universe, they refer to something like this picture and say how it's pretty much relatively uniform, with no significant variations in density or temperature across vast distances, making it look kind of smooth, as in there's no big major clumps or irregularities or anisotropies. You know, isotropic means like the same in every direction, right? So anisotropy would be where something is not the same in every direction. So this sort of homogeneous nature or isotropic nature of the universe is what people refer to as the smooth universe. And you might hear things like the early universe is very smooth, and they've been studying it for a long time with something like the CMB photons, and they still mostly find that it's smooth. But actually the devil is in the detail again, in the sense that you will see how we actually will delve deeper into the quote-unquote smooth universe and find that there are anisotropies, and we actually mentioned them when we were talking about the cosmic inventory, because we said that the anisotropies are actually dependent or very sensitive to dark matter. So the fact that there is any anisotropy is sort of could have very interesting implications and exciting implications for the dark matter people as they research that more. But it's definitely still sort of an evolving topic. And the smoothness that we speak of is also when you look at very large scales. So like smaller scales, like galaxies and clusters of galaxies are of course not smooth, but at larger scales, it looks smooth. Or in other words, a very uniform temperature of these CMB photons across the sky with only very tiny fluctuations. But is there more to the story with fluctuations or not, is something that people are looking into or have looked into, and those types of developments will lead us into further details. But overall, they consider this to be quote unquote smooth or uniform temperature across the sky. Okay, so that's what smooth means. Yeah, temperature of these photons considered to be smooth, yeah, over large distances. And that temperature is around, I mean, you can see it in the scale there. I think it's in microkelvins, but it's around 2.7-ish kelvins, I think. I forget the error. There's an error on the temperature, of course. You know, I was trying to find it. Maybe I can find it. Let me see. I think it's like 2.7 plus or minus the temperature of the CMB, because they've done several measurements. It's not just from one measurement that you would know this temperature, you know. Oh, nice. I got 25 likes. Can we get 30 likes? Yay! Can we get 30 likes? Oh, here we go. Hopefully I'm getting closer. Oh, there we go. We talked about the temperature of the CMB photons when we talked about the cosmic inventory. When we talked about the cosmic inventory, we actually mentioned it, but I'll say it again. The temperature of the CMB photons has been measured extraordinarily precisely. So this is what I was saying. Like, it's not just that this has been measured. It has been measured a lot. So you can look up something like the COBE satellite, that is COBE, COBE satellite, FIRAS instrument, FIRAS, FIRAS instrument. So this instrument has measured this temperature to be with an extraordinary precision. And the temperature of the CMB photons is 2.725 plus or minus 0.002 kelvins. And there's a paper by Mather et al. From 1999, for example. The author name spelling is Mather. So basically, do you know about the Boltzmann constant and things like that? Basically, if you have the energy of something, you can associate a temperature with it. We also know it observationally because the spectrum of the CMB has been measured so accurately. Well, okay, so let's see. Basically, when you have the energy of something, you can associate a temperature with it. You can, Whoops, my iPad has died now, so I can't see the things anymore. So I should do the math for that for you sometime. Basically, it's not very difficult. You could look up the Boltzmann constant. It's generally given the symbol of KB, small k subscript capital B, Boltzmann constant. So actually, when we talked about the cosmic inventory, remember we were saying that basically the zero order the zeroth order distribution function for these photons will follow the Bose-Einstein equation, or the Bose-Einstein function for the photons, because photons are bosons, and basically at the zeroth order the CMB is mainly just the photons or the bosons, although at higher order perturbations there might be some other features like baryons or dark matter, basically. So we had kind of mentioned about that. So basically the photon energy density depends on time via the scale factor, but has no spatial dependence. This is because we have used the zero order distribution function, the Bose-Einstein function, for the photons. In fact, there are small perturbations around this zero order distribution function. These do have a spatial dependence and correspond to the anisotropies in the CMB. So if you consider the CMB to be just photons and say that you're going to do no spatial dependence, Bose-Einstein function for them, then you get a certain view of them. But turns out in the more detailed view, there is a spatial dependence, and those come from anisotropies, probably because of other things like baryons or dark matter. But basically, as far as these, it's photons. So photons have an energy, right? And from that energy, you can get a temperature associated with these photons. So instead of saying it in terms of the energy, people report the result in terms of the temperature. It's kind of like the same thing, basically. So it's not a huge deal. We can go over the math at some point. Yay! So that was a little bit more about the universe. It's nice to talk about the universe at a regular basis, because it's very incredibly interesting. But yeah, let me adjust my heat. It's very cold. It's gotten really cold, and I might have to go to bed soon here. Might have to go to bed soon here. Very, very cold. Wait, what? How did we get on Epstein Island now? Stephen Hawking and Hawking radiation. We should talk about that sometime, yes. I didn't know that, Ajay. You're the first one to tell me. I do know about Hawking radiation and black holes. black body radiation of black holes, but did not know about the Epstein Island thing. People believe that he got up from his wheelchair. His AI chair was hacked. Well, all right. Hope you guys enjoyed today's lesson. Yeah, I came over here. I was looking stuff up from the cosmology book to find like a good way to talk about the CMB after you asked about that. But then I come over here and y'all have now gone off to Epstein. You are a crazy bunch. Thank you for being here. Can I get 25 likes, please? We're on Epstein. बाजी तुम्हें हिंदी आती है? हाँ जी, बिल्कुल आती है. आपको आती है? So let's see if we can get 25 likes. And please like, share, and subscribe. And please share with 1 billion friends. And please continue to come to the lives and comment and watch the full video once it's uploaded. Thank you so much in advance. Thank you for your comments. Thank you for the participation. Welcome to the live and thank you for being here. Please rewind and watch it from the beginning if you missed the first part. And I'm shaking because I'm cold. And can I get 25 likes? One more like would be 25. That would be good. And yeah, thank you so much for being here. I'm gonna go live again tomorrow. See you tomorrow. Yay, Ben. Oh, thank you. Ben, thank you so much for being here and checking in and commenting. Thank you very much. Appreciate you. लेकिन आपके बोलने में एक अकड़ है. आप normally बोलने का try करो. Well, Hindi is not my mother tongue, Ajay. And I'm reading your comments. See you tomorrow. Hi, Ben. See you next time, Audrey. Thank you. Good night. Thanks for the live. Fun and informative as usual. Thank you. Man, kind of want a sandwich now. Oh, we never shot the shit. Who taught you? Well, I took a couple of years of Hindi in school and then I watch movies, so of course. And when I'm with my friends, it flows a bit more naturally. But if I'm in the mode of like English only, then, you know, it really depends on my code switching, how good I get at a language. Right now, I'm sort of in the mode of like teaching the material in English, so you're not getting that side of me. But when I hang out with my Indian friends, then my accent is different, my Hindi is better. I teach them Bengali, my mother tongue is Bengali. So Hindi is nothing new to me, but it's not exactly my first language either. So I don't like when people expect that I should be better at Hindi. You should expect me to be better at Bengali. इतनी हिंदी तो यहाँ साउथ बॉम्बे के लोग नहीं बोलते जितना आप बोल रही. Who taught you? Oh yeah, I already answered that. South Bombay में? Oh wow. Well, I learned Hindi in school and also by watching all the movies. So, oh, and I think you asked me my favorite movie. My favorite movie, I don't think has much to do with science. So I have a science brain and like my work has to do with science and STEM and math, engineering. Mostly I love the pure sciences, you know, physics and all that, physics, astronomy, chemistry. More at this point, maybe physics, cosmology, astronomy, and astrophysics. But so that's my science brain, or more of a work brain. In my personal life, I do more things and interested in other types of topics as well, including history, literature, other cultures, stuff like that. So, anyway, I have a lot of movies that I really like. Probably my favorite movie might be maybe like Devdas, actually. The Sanjay Leela Bhansali one. You're a Bengali, they are the sweetest people I know. Yes, of course I'm a Bengali. Of course. Of course, my friend. Oh my god, you guys should look at the outside. Once it charges more, I will show you. There is so much snow. It snowed a ton here, guys. It's like a white wonderland outside. Like, it looks bright outside even though it's nighttime because of the snow. Tomorrow morning when I wake up, I'm going to show you guys the snow. I'll go live just to show you the snow, and then we'll of course talk about astronomy and cosmology probably, because why not? But yeah, Devdas is more of a rom-com. Devdas is not a rom-com, it's more like a romantic tragedy, right? Well, I like rom-coms. What do you mean? I love romances, rom-com. In this case, it's a romantic tragedy, but it has like the big drama and all that. So I was just looking back into my childhood to see what might be one of my favorites. So to name one, that is one. There are other movies I like too, but Devdas is a big one. I think it's associated with my childhood, and I loved, you know, the big scenes and songs and emotions. So that's why I like it. I have not seen Oppenheimer. I don't like to watch movies about work, guys. Come on. Oppenheimer is like a colleague, so no. I like to relax. I believe in relaxation as well, guys. Come on. I like to see a juicy romantic drama where everybody dies. Well, actually, no. I don't want people to die in the movies. I get very sad. I get very sad. I don't want them to die, but sometimes they do. Hi, Fuji baby. তুমি সোনা. Hi, Fuji, come. আসো খাবে আসো। কত ভালো ছেলে। আসো বেবি, কত ভালো তুমি। কত ভালো তুমি। Come, baby. ছোট ছেলে মেয়ে তো, ছোট ছেলে মেয়ে। কিচ্ছু খেতে পাইনি। আসো। কিচ্ছু খেতে পাইনি। আসো। No, 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 not like that. Um, no, 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 no. I was just joking. I don't like when everybody dies. I think Devdas is like probably the main one that I like where the main character dies, but I don't know. Just normal romantic dramas, stuff like that. Favorite rom-com. I think I used to watch Kabhi Khushi Kabhi Gum a lot. I probably watched K3G like every Sunday with my cousin for a while. That was probably a favorite. These days, I don't have really much of a favorite movie or show anymore because I don't watch movies and TV shows that much anymore. I can try to think what was the last movie I watched. I think it was Veer the Wedding on Netflix, and I don't think I liked it that much. I think at this point I kind of don't really relate to a lot of that content sometimes, or the content that's packaged into a movie, because it seems very superficial. Favorite show, I would say, I think I liked Virgin River was one show I liked. But yeah, I think like the movies that have a lot of drama and a lot of grandeur is, at least it's like making you feel something in a short period of time, relatively, like within 2-3 hours you feel a lot of emotions. Probably that's the reason why I liked certain movies that make you do that. That's about it. That's about it. Probably needed a little bit of romantic in my life, and it came in the form of the movie. You know what I mean? Okay, I need to charge my iPad because it's completely dead now. Thank you, everybody. Rewind if you're coming in. You can see the full episode from today. From today.